In this chapter, we'll be talking about nucleophilic substitution reactions of alkyl halides. So we'll be looking at reactions of alkyl halides overall, but focus on nucleophilic substitution. And then in later chapters, we'll talk about many other reactions of alkyl halides. In this video, we'll be looking at a brief introduction and then some general information about nucleophilic substitution reactions. As we think about the reactivity of alkyl halides, we need to keep in mind that the carbon-halogen bond is very polar. So the dipole does not have a huge impact on intermolecular forces, but it definitely has a big impact on reactivity. So because the halogen is pulling away electron density, that leaves a carbon with a partial positive charge, so we have an electrophilic carbon. Now, many of the reactions that we'll be looking at involve a nucleophile adding to this position, pushing away the halogen as a leaving group, so that what we're looking at then is an overall substitution. But it's also possible for this group to act as a base to grab off a hydrogen that is on the carbon adjacent to the carbon with the halogen. If this acts as a base, grabs off this proton, these electrons can come here, kick out the halogen as a leaving group, and we are doing an elimination reaction. The reason why these reactions can work is because we need to think about a Lewis base. So remember, a Lewis base is an electron donor, and Lewis bases might act as a Bronsted-Lowry base, which means it grabs a proton, or they could act as a nucleophile. So if this is our alkyl halide substrate, and we have a Lewis base that has a lone pair of electrons, either it can approach the carbon bearing the leaving group, form a new bond with that carbon, and push away the halogen, leading to the substitution product. Or if this is too difficult, rather than trying to fight its way in, it might settle for, well, I'm just going to grab one of these protons. And so it can grab a proton, allowing these electrons to come in here, push away the halogen, leading to elimination. So both substitution and elimination are very, very useful reactions of alkyl halides. In this chapter, we're going to focus on substitution. Next chapter, we'll take a look at elimination. We can see what's similar about them, but we'll talk about the differences that ensure that you get substitution rather than elimination, or elimination rather than substitution. As we think about nucleophilic substitution reactions, we might have a nucleophile that has a negative charge, and this can react with some alkyl halide or other groups where Lg stands for a leaving group. If we're starting out with a negatively charged nucleophile, then we will end up with a new bond between the nucleophile and the R group, and we're going to have our Lg leaving with the pair of electrons. On the other hand, if our nucleophile is neutral, when it shares its electrons, it will end up taking on a positive formal charge. And we still have our leaving group has left. So here's a few examples. We might have cyclopentyl chloride, and we can treat this with sodium cyanide. Now remember what we reviewed way back in chapter 1, ionic versus covalent bonds. When we're thinking about sodium cyanide, we have a sodium cation, and then we have cyanide as the anion, a negative formal charge on the carbon. This is the nucleophilic atom. So when this reaction occurs, we are going to end up with this, where the carbon is connected to the carbon that used to be connected to the chlorine. This will still be triple bonded to the nitrogen. And our byproduct then, we're going to make sodium chloride. The sodium ion is still just floating around in solution. We've kicked out chloride ion, and so they can hang out together as a salt. Here is another example. If we take T-butyl bromide and we react this with ethanol. Now we're talking about all covalent bonds, and so that's important to pay close attention to that. Remember, in this example, we had a nucleophile with a negative charge, and so we got this as our product. Here, we have a nucleophile with no charge. So our immediate product is going to look like this, where the oxygen is connected to the CH2CH3, still connected to the hydrogen, and that oxygen has a positive formal charge, and then this will go through a proton transfer to lead to the final product. And so here we will end up with OCH2CH3 plus HBr as a byproduct. So the bromine has left, and also the hydrogen has been removed. We'll talk later about how that happens, but for now, I just want you to see the overall change. There's a wide variety of nucleophiles that can be used. So if we have an alkyl group with some leaving group, it can be converted to an ether or an ester or a sulfide or a nitrile, or this is called an azide. And so there are many functional group interconversions that can be carried out through nucleophilic substitution. So as we think about our nucleophilic substitution reaction, let's focus on the substrate. In particular, let's focus on the alkyl portion of the substrate. So we can carry out these reactions with a methyl, primary, secondary, or tertiary alkyl halide. All of these will undergo nucleophilic substitution reactions. What if we have a double bond or an aromatic ring? One of the requirements for nucleophilic substitution is that the X must be connected to a carbon that is sp3 hybridized. So here we have an alkene. These carbons are sp2 hybridized, but we have more carbons before the chlorine. So chlorine is connected to an sp3 hybridized carbon. So this just counts as a primary alkyl halide. And so this will undergo nucleophilic substitution. Here, our chlorine is directly connected to the alkene carbon, so that means it's connected to an sp2 hybridized carbon, so this one will not react. Here, our bromine is connected to a carbon that's connected to a benzene ring. This carbon is sp3 hybridized, so this compound will undergo nucleophilic substitution. So this halide is primary, and it's also called benzylic, because the bromine is connected to a carbon that's connected to the benzene ring. So primary and benzylic. And with our last example, bromine is directly connected to the benzene ring. This carbon is sp2 hybridized, so this will not undergo nucleophilic substitution. As we think about the structure of our R group, it's been shown experimentally that the relative rate follows the trend that tertiary are more reactive than secondary, which are more reactive than methyl, which are more reactive than primary. So for any alkyl halide, we'll be looking at this trend in reactivity. This is an unusual trend, but when we talked about conversion of an alcohol to an alkyl halide, we saw that that reaction can happen through two different mechanisms. Well, if these alkyl halides underwent different mechanisms, that would be a possible explanation for why we see this unusual trend in reactivity. Next, let's think about the leaving group portion of the substrate. And we're starting out thinking about halides. And so what is going to make this a good leaving group? There are a couple ways to think about this. One, we can focus on breaking the CX bond. If we keep in mind the difference in size If we are thinking about a carbon-fluorine bond, those atoms are similar in size, so there will be effective orbital overlap. If we're looking at a carbon-chlorine bond, chlorine is bigger, so the orbital overlap won't be as good. We can think of this as a longer and weaker bond. A carbon-bromine will be even longer, and then a carbon-iodine bond will be even longer because iodine is so huge. So the orbital overlap isn't very effective. Iodine barely knows the carbon is there, and so breaking this bond is going to be a lot easier than breaking the others. Another way to think about this is that when a leaving group leaves, you form X minus. So let's think about I minus versus Br minus versus Cl minus versus F minus. And we actually compared these when we were talking about relative acidity. If we think about the relative acidity of HX, we're looking at the bond strength, how easy it is to break this bond, similar to what we just said here. And then we're also thinking about how stable is the conjugate base. Even though fluorine is the most electronegative, and then the electronegativity decreases in this direction, because we have such a big difference in size, size is what matters. This is so big, it can easily bear that negative charge, which makes this a very weak base, which makes it very stable. In comparison, fluorine is going to be the strongest base, and so it is going to be the worst leaving group. So taking into consideration the ease of breaking the CX bond and the relative stability of X minus once that bond is broken, when we're thinking about the different leaving groups, alkyl iodides are more reactive than alkyl bromides, which are more reactive than alkyl chlorides, which are more reactive than alkyl fluorides. So when we think about leaving group ability, we need to keep in mind that leaving group ability is inversely proportional to basicity. So a strong base is a bad leaving group. A weak base is a good leaving group. So we want weak bases to be our good leaving groups. Although we are focusing on alkyl halides, there are other groups that can act as leaving groups. Keep in mind, we just said that a good leaving group is a weak base, and a weak base is the conjugate of a strong acid. So one of the acids that you learned about in general chemistry is sulfuric acid. That's a nice strong acid. And then an organic acid that's kind of related to sulfuric acid and even stronger than sulfuric acid is called para-toluene sulfonic acid. Para-toluene sulfonic acid, and it's abbreviated tosic acid. Now, this is an even stronger acid than sulfuric acid, so that means that its conjugate base is going to be a really good leaving group. So we can prepare a tosylate as a leaving group by reacting an alcohol with tosyl chloride, which looks like this. And then this will give, this oxygen will be connected to the sulfur, which is connected to the benzene, connected to the methyl. So this is abbreviated OTS. So this whole group is the OTS group, the tosylate group. So then the reaction, once you have your tosylate, then this can react with a nucleophile to give your R group connected to the nucleophile and the tosylate as the leaving group. Now, tosylates are even better leaving groups than halogens. This is not the most efficient approach because you are adding a really big group onto a molecule just to kick it out again. But if we're just doing our reactions on paper, then recognize a tosylate as a good leaving group.